Okay, so this time it's time to start relating all that graphing stuff to motion. But to do that, first we need to understand one other graphing aspect. So this is a straight line. Any straight line on a graph has a formula for that line. Now I've already put in some things like its beginning coordinates, its ending coordinates, and its slope. That'll just help us along a little bit because the next formula we need to understand is the formula of a line, which is nothing more than y equals mx plus b. And again, this should be review for everybody. But if you don't know, this is a y coordinates, this is the slope, this is x coordinates, this is a origin point, or y-intercept as they call it. So really what this is telling you is how much x has gone by, especially if it's time, times the slope, plus wherever it started from will tell you wherever it ends on the y coordinates. Okay? So it's real simple to do. Let's take a look at that. In fact, I'm going to rewrite it ever so slightly. And I'm going to write it as y final is equal to mx plus y initial. Now, I did that because, like I said, that b is really your y-intercept. So it's really just wherever the line starts, okay? And then x is how much is in between times the slope will give you your final y position. And we can see in this one, it starts with a y of 1. Okay, so we're always going to be adding 1. And then our slope is going to be 1 as well. So we're going to multiply something times 1. And so let's look if I wanted to go, let's say I wanted to go and see where it was after 6 in the x direction. Well, since I moved 6, I'm going to now put that down here for the x in that. And then I just mathematically solve that. 1 times 6 is 6, plus 1 is 7. So that means for this one, my YF is equal to 7. And you can see that's right. So if I go over 6, I'm going to have to go up to the 7 marker to find where it is on a line. And they teach you that in all of these grade schools and things, saying, oh, just remember that. But now the fun part of physics, we get to relate that to something real. Because here's the deal. We don't have just a x and a y. Yes, we have those coordinates, but we put values to them. So what are we going to put a value to it? Well, let's do a position versus time graph, which means up here on top, we're going to have distance for our y, and we're going to have time for our x-axis. Now, this helps us out immediately because what we know is we don't have a negative time, which means I can now do away with all of these over here. I don't need any of that part of my graph now, okay? I'm going to erase that so I can still do that, but you don't need those anymore because time only goes forward. Next thing I can do is I can say, okay, so what I'm really saying about this is my my times that elapse times my slope plus my origin spot. So where did I start my movement? But there's something else we need to realize about this. That slope, what is our slope on a distance versus time graph? Well, if we look at it, remember that your slope or your distance is made of meters and this is seconds, right? And so if our slope now is equal to our change in distance over our change in time, well, that's exactly like velocity. Velocity is equal to a change in distance, also known as a displacement, over time, right? So now we know that we can even change something else on this formula down here, and we can say, okay, well, I don't need it to be position, I don't need it to be y. I can say that it is my final destination is equal to my velocity times the time that it takes plus my initial spot. Some people call that the start. So you can do a d of small I or a d of a small s. But it doesn't matter. You're going to get the same values. In fact, I can mathematically solve this around and say, wait a minute, this is v is equal to, and you end up with df minus di divided by time. And another way of writing that is just delta d divided by t, right? So this is all the formula, and that's what it tells you. And this is really, really helpful because now I can actually use all of this information. It's just not some funky stuff on a graph. So I can say, look, I started my movement here at one position above whatever my origin is, 1 meter above my origin. Maybe this was my house and this is where I started riding my bike. I rode it at a steady pace for 7 seconds, right? For 7 seconds I rode it, and that managed to get me 8 meters away from my house. So now our motion tells a story. All of this now has a point. Yay! So let's just take a look at one of those stories. So we have another graph, but notice this one is distance over time. Even though these times are funny units of it, it's a lot of time going by because you go through a lot of seconds in a minute. Okay? But then we're talking about a bike rider here. So what we can see is, look, when I start off, even without doing exact numbers, I started at my origin point. I started with a positive constant velocity, right? I know that it's constant because it's a straight line. I know that it's positive because it's tilt upwards, right? That's our slope. We have a positive slope. So we started moving away from our origin, but then at some point we stopped. Maybe you took a rest. You got so far away, you're like, I'm a little winded. And then you wanted to start to go back. So you had a negative velocity, but it was still constant. So notice that you're going back towards your house. You didn't arrive yet at the end of this graph, but you can see all of this on a velocity or on a position versus time graph, which tells you things like the velocity, and you can calculate the velocity here, here, and here. Notice here the velocity is 0, meaning you're not moving. And you could actually figure out using that formula where you ended up at any given time on one of these lines. And that's how it works in the real world.